Hi all, thanks for coming to the fifth session. While we wait a minute for David to switch browsers, I'll just remind you that although we probably won't have time for questions during this session, there will be a dedicated time for discussion in the discussion poster session just outside in the lobby right after the session. So I truly invite you all to attend. I see David is here, so yeah, our first talk will be the product of Gaussian matrices is close to Gaussian by Yi Li and David Rudroff, and yeah, David will be giving the talk.
Okay, can you guys hear me? And can you see the slides?
Yes.
Okay,
I hear you perfectly. Thanks, David.
Great, yeah. So this is the product of Gaussian matrices is close to Gaussian, joint work with Yi Li. So in this work, what we do is we study the product of two or more Gaussian matrices. There are applications to this in regression. The design matrix is random, wireless communications, stability of large complex systems, applications in physics, and so on. For example, in regression, your goal is to find a vector x to minimize the Euclidean norm of ax minus b squared. And sometimes you can also add this regularization term, lambda times the squared norm of x. And in a number of applications, this design matrix A is very tall and thin. Okay, so it has many more rows than columns. And in some applications, it's also Gaussian. And one way of solving this problem is with what's called the sketch and solve paradigm, where you choose a very short and fat Gaussian matrix S, and you replace A with S times A, and you replace B with S times B. And now you can see that S times A is a product of a short and fat Gaussian and a tall and thin Gaussian matrix. And so it's important to understand the distribution of this matrix. Also, if B has multiple columns, or even one column, you see that S times B is a product of a Gaussian matrix and a Gaussian matrix if B is also Gaussian. So there are a number of applications that are described in more detail in the paper. But in this limited amount of time, let me just get into the formal problem setup. So we look at the product of R Gaussian matrices, G1 through GR. We're going to think of R as a constant. And so each Gaussian matrix GI, it has DI columns. Okay, and you can multiply these matrices together. They have the right dimensions. The number of rows of the product we're going to denote by D0 or P, and the number of columns of the product is Q. And you can think of P and Q as being much smaller than these inner dimensions. This is when our upper bounds will be the most meaningful. Okay, so the question, we also have a technical condition that dr minus 1 equals d1. When we have two Gaussian matrices, this statement is vacuous, but we need it for more than two Gaussian matrices. And the main question we ask in this talk is this product matrix A sub R close in total variation distance to a single Gaussian matrix A sub 1? These are normalized properly, so G1 through GR are standard IID Gaussian matrices, and yeah, so that's the question we look at, and this is what we show. We show that the variation distance between the product of R Gaussian matrices and a single Gaussian matrix is at most a constant times the sum from I equals 1 to R minus 1 of the square root of PQ over DI. Now, let me just remind you what these things mean here. So remember, we have a constant number of Gaussian matrices R. C1 is a constant. And so what this is saying is P is the number of rows in the product. Okay, so the number of rows of the final Gaussian matrix. And Q is the number of columns. And so what this is saying is, as long as all these intermediate dimensions, di, are larger than a constant times P times Q, then this variation distance is less than 2/3, say, or less than an arbitrarily small constant. So the intermediate dimensions need to be large enough and larger than the product of the two n dimensions. And we show in some sense this is tight, though we don't have a complete characterization. We show conversely that, okay, so if we look at this expression, if this expression here holds, then the variation distance is at least 2/3. Now, what is this expression? Well, remember, R here is a constant number of matrices. So you can think of replacing the sum with a max. And C2 to the R, that's just a constant. And if P equals Q, this number of rows and number of columns in the product, then this denominator is just P squared. And so this is saying that all the intermediate dimensions need to be at most P squared. If all the intermediate dimensions, if there's an intermediate dimension that is at most P squared, then the variation distance is at least 2/3. Whereas our upper bound says that if all the intermediate dimensions are at least a constant times P squared when P equals Q, then the variation distance is less than 2/3. So we get a dichotomy up to a constant factor, at least when the number of rows and the number of columns in the product are the same up to constant factors. There are a number of nice open questions here. You can see that we don't handle super constant number of matrices, R. We're getting an exponential dependence on R. We also have this max and min in the denominator that doesn't match what we have in the upper bound. So yeah, there are great questions here. Let me just quickly go over the upper bound. So a natural attempt might be a conditioning argument where you, let's just look at two Gaussian matrices, G1 times G2. And you want to reveal the entries one by one. And you want to maybe argue that conditioning on the previous entries you've revealed, maybe a new entry you look at behaves like an independent Gaussian. This way you can show that overall the product is close to a Gaussian matrix. But the issue is the entries are correlated in the product. For example, here's G1 times G2. If I look at these two entries I get, this blue and this yellow entry, well, if the blue entry is large, it might indicate that this row in G1 is large. And therefore, it might also indicate that the dot product with this second column in G2 is also large. Okay, but maybe you could try to fix that by conditioning on all the rows and of G1 having the right norm and the columns of G2 having the norm that you would expect. But then you could look at 2x2 submatrices, and then you run into the same kinds of issues because if the blue, yellow, and green dots here are large, well, this might mean the first row of G1, this ith row, is correlated with both of the columns in G2, J and J prime. And because this green entry is large, well, maybe it means that the I primed row of G1 is correlated with the jth column of G2, which is then in turn correlated with the ith column of G1, which then maybe makes this orange entry large, right? So, there are these 2x2 submatrices that really look different in the product than in a real Gaussian matrix where they would be independent. And we use actually precisely this intuition to prove our lower bound. But let me explain how we can get the upper bound. The key idea we use is this result of Jiang and Ma. It's a very cool result. If you don't get anything out of this talk, please remember this. So if you take a d by d Gaussian matrix versus a d by d orthogonal matrix, so unit norm columns and rows, orthogonal columns and orthogonal rows, well, they don't look anything like each other, right? The singular values of the orthogonal matrix are all 1. A Gaussian matrix, they're certainly not. But if you look at small enough submatrices of the orthogonal matrix, then suddenly they look Gaussian. And more precisely, what Jiang and Ma show is that the KL divergence between a P by Q submatrix of a D by D orthogonal matrix with 1 over root D times just a P by Q matrix of standard Gaussians is actually at most P times Q over D up to a constant factor. And applying Pinsker inequality, this implies the variation distance is small, a constant times square root PQ over D. So basically, if P times Q is less than D, then I get, low constant variation distance. So I can, take, n by 10 by 1 submatrix, or I can take a, root n by 10 by root n over 10 submatrix. And these submatrices of an orthogonal matrix, they look Gaussian. And we can use that to actually critically in our proof. So I'll just give the whole proof for the product of two matrices. on this slide. So here I have G1 and G2. G1 is P by D, G2 is D by Q. And I'm looking at this product matrix, A2. Okay, same notation as before. It's G1 times G2, and they're normalized appropriately. G1 and G2 are standard Gaussian. And A1 is just a standard Gaussian matrix, which is P by Q. I want to show A1 and A2 are close. What do? I take G2 and I write it in its singular value decomposition. U sigma V transpose. U has orthogonal columns, sigma diagonal non-negative, V orthogonal rows. Okay, I start with A2. It's 1 over D times G1 times G2. Let's take G2 and replace it with its singular value decomposition, U sigma V transpose. That's all I did. And now, look what we have here. We have a Gaussian matrix, G1, times a matrix with orthogonal columns U. That's the same thing as a Gaussian matrix by rotational invariance. So that's G sub PQ sigma V transpose. That's the dimension because U has Q columns since it came from G2, and G1 has P rows. Okay, and now is the main idea. So like, you should never look at a Gaussian matrix the same anymore. You take a P by Q Gaussian matrix, and that's the same thing as a P by Q submatrix of an orthogonal matrix, provided that P and Q, their product is at most D, as we said. And it's up to this 1 over root D normalization. So here's where we apply that Zhang and Ma result. And then a P by Q submatrix of an orthogonal matrix, just using unitary invariance of orthogonal matrices, this is the same as a random P by D submatrix, P by D orthogonal matrix times a random D by Q orthogonal matrix, U. And then U sigma V transpose, that's the same thing as the SVD of some Gaussian matrix, G2, because it has random left singular vectors U. And now I have orthogonal matrix times G2, and the product is again Gaussian, and now I get my other Gaussian I get a Gaussian matrix. So the product of two Gaussian matrices is close to a Gaussian matrix. We just lost this one step in variation distance. And yeah, you can apply this idea iteratively, generalize it to the product of R matrices. I don't have time for that, but it's, yeah, similar idea. And as I said, the idea behind the lower bound is to carefully look at the expectation of we use the Shadden 4 norm. It's the, it's just the sum over 2 by 2 submatrices of the products of the entries. Yeah, so we use that, we carefully bound that, and that, I'll stop the talk there. Yeah.
Thanks, David.
Okay.
Okay, so our next talk will be Singularity of Random Integer Matrices with Large Entries by Sankrith Rao Karingula and Shachar Lovet. And Sankrith will give the talk. Thanks, Sankrith. Go ahead.
Good morning, everyone. That was a nice talk by Woodruff, and thanks for attending my talk. I'll be talking about the singularity of random integer matrices with large entries. So to begin with, the overview would be, I'll just define what singularity probability is and explain the known results and mention our main result and explore some connections to coding theory and just summarize the talk. So to begin with, random matrix theory. So singularity probability, let's say you fill a n cross n matrix with entries from some alphabet uniformly at random. And now you want to know what's the probability that this is singular. So that I call as Pn. So it's essentially you just have a square matrix, you're filling each entry IID at random, and you want to know when is it singular. Right. So the first result was by Komlos, and this was a non-trivial result already, and it was very interesting. So it's like he looks at plus minus one alphabet, and he and he shows that this singular probability is lit low one, right? So, and the lower bound is like just like a trivial lower bound, just of two columns being equal, like 1 by 2 raised to n kind of lower bound. So there is a huge difference between the upper and lower bounds on the singularity probability. So after 30 years, Komlos and Zemeridi, they significantly improved this bound and showed that this singularity probability is less than or equal to c raised to n for some constant c. And the constant they came up with was like 0.995 or some really close to one number. And then there was a series of works for improving the constant. So first there was a talk by there was a paper by Tao which improved it to 0.75, and then by Borgain which improved to 1/√2, and then like recently there was a work by Tikhomorov who found the best constant. So he showed that this is upper bounded by half plus little o 1 raised to n. So this is the best possible, as just the probability that like if you have two columns which are equal, then you already get like the matrix is singular and its probability is 1/2 raised to n. So this is the for plus minus one alphabet. So we have like we completely understand, like we have an closely matching upper and lower bounds. And then slightly more general distributions, like for sub-Gaussian random entries, there's work by Rudolfsen and Vershinin. So they extend the Kahn-Komlos-Zemeridi result for all sub-Gaussian entries, where and they get like the singularity probability is less than or equal to c raised to n. So this would like if the alphabet size grow, like I'll explain later on, like if the alphabet size grows really big, this wouldn't help us prove the right kind of bound. So the main question, like a more broader question we can ask for more general alphabet is like, if I have an n cross n random integer matrix with entries chosen from minus m to m uniformly at random, can we show that the probability that the matrix is singular is m raised to minus cn for some constant c? So this is known when like m is constant and n goes to infinity, and also known for n is constant, like where the length dimension of the matrix is constant, but the alphabet goes to infinity. And what if both of them are large? So here also there's a very interesting work by Wempala, Wang, and Woodruff. So they prove this result, like they prove that this singular probability is bounded by m raised to minus cn. But instead of the uniform distribution, they look at like they look at this plus minus one kind of distribution, but they look at multiple copies of it, like m different copies of this distribution on minus 1, 0, 1. So this this is slightly easier to deal with because it's more, you have better Fourier tails, because when you're having a convolution of many distributions, like if you look at the Fourier transform, it'll be a product, and so the tails would be very well behaved for this distribution. But we in this paper, we look at the more general distribution, where you're looking at a fully uniform distribution from minus m to m, and we ask the same question, like what is the probability that your matrix is singular, and can you show it's upper bounded by m raised to minus cn? So all the previous works, they either showed for like m is like the alphabet size is constant, or the dimension is constant, and or if m and n are both growing, they looked at like bounded tail behavior kind of distributions. So we look at the hard case of uniform distribution, and also recover the result when both m and n are large. So this is the main result of the paper. Just the singularity probability being bounded by m raised to minus cn. Since this is a short talk, I won't go into the proof details, but I'll be happy to discuss in the poster session. And the other thing is like they can connect this to nice results in coding theory, and it opens up many interesting questions. One question is like MDS codes, like so. MDS codes have the best possible trade-off between like message length, code word length, and minimal distance. In particular, like we have the singleton bound, which bounds the minimum distance to the like redundancy plus one, upper bounds it. And MDS codes exactly achieve this bound. And if you look at the generator matrices of MDS codes, then you'll get like a k cross n matrix where every k cross k minor is non-singular. So now you can ask this question as to what kind of alphabets support such a matrix MDS structure. So for finite fields, this is a very well-known question. So it's completely like almost understood. Like the up to a factor of 2, we can just read Solomon codes will achieve the optimal like near up to a factor of 2 alphabet and size. And in general, like you need over prime finite fields, you need the field size to be at least linear in n. But using this result, we can show that like over integers, like they exist over much smaller alphabet. In particular, just we can just by a union bound, we can show that there exists MDS matrices where like the alphabet size is poly n over k. So note that like in coding theory, the typical regime, the rate is like a linear in the distance. So n by k would just be like a constant. So we could say that we could prove that like MDS codes over integers exist with just constant alphabet size. This was in stark contrast to like finite fields. And this is like a first step towards a more broader study of codes over integers and trying to look at more. We have a general conjecture in the paper rather than like having all the minors being non-zero. We can look at different like tree codes or different codes. We can put it in different minor structures and ask like which alphabet size will support that. So this is one connection to coding theory, and this opens up many interesting questions. For instance, like we can ask like a general distribution conjecture, like rather than minus m to m, if you have any distribution, a uniform distribution, rather than a uniform distribution, if you have like your distribution L infinity is bounded, can you still prove such a singularity bound on that? And explicit constructions of such MDS matrices would be very interesting. And the algorithmic questions, because right now we are defining, rather than defining it as a vector space, we are defining it as a lattice. So we run into this question of like, how do you encode and decode? How do you use these for actually encoding and decoding? Because if you add many vectors, or if you take a large coefficient vector, then the integer size blows up. So we have this nice phenomena of like constant alphabet size being able to construct these matrices, and how would we come up with the algorithmic operations? And so I think I'm close to my end of the time. So
yeah,
thank you very much.
Thank you. Thanks, Sankrit.
Yeah.
Okay. So our next matrix talk will be a smooth analysis of the condition number under low-rank perturbations by Rikav Shah and Sandeep Silwal. And Rikav, go ahead.
Thank you. Let me go ahead and share my screen. All right, can everyone see the presentation?
Yeah.
Great. Yeah, okay, so I'm Rikov, and I'm at Berkeley, and I'm talking about the smooth analysis of the condition number under low-rank perturbations. This is joint work with Sandeep Silwal, who's over at MIT. So the problem to remember is, how does the condition number of a matrix behave under low-rank perturbations? So the condition number of a matrix is just the ratio of the largest to smallest singular values, has obviously a lot of algorithmic implications for the runtime of algorithms in practice. And we on this paper are considering a bad condition number, or a condition number to be bad if it's more than polynomial. So we are interested in showing that condition numbers are at most some polynomial in n. In the smooth analysis framework, we're trying to deal with a problem that, or the conundrum that in practice, it seems that matrices are more well-behaved than they should be, or they're oftentimes well-conditioned, and the smooth analysis tries to discover why. And one explanation is that oftentimes in practice, the matrices which we observe are some true signal plus some noise matrix. So the sort of classic result in this space says that if you start with an arbitrary matrix and add a dense random Gaussian ensemble with IID Gaussian entries, you end up with a matrix whose smallest singular value is not too small. It's like 1/√n. And this result has been generalized to a number of different distributions, not just Gaussians, but any sub-Gaussian, and even where the entries have different distributions, but crucially are still independent. And our result seeks to generalize this to low-rank perturbations. So the motivation, there's a couple different motivations. So one is, in practice, dealing with low-rank matrices can be nice. You save some space. You can store this factorization. And also in practice, some of the measurements have some relationships, or some measurements might be computed based on each other. So it's perhaps natural that your noise, which is being added to your data, satisfies some relationship, which may result in this noise matrix being low rank. And if you want to construct these matrices explicitly, you require fewer random bits to do so. So our result is very much in the same line, or the same vein as the prior results in the dense case. And it says that if you start with a matrix of rank n minus k and add a rank k random matrix to it, you end up with a smallest singular value, which is not too small. In particular, it's not too much smaller than the smallest positive singular value of your original matrix. And that dependence is sort of necessary. So you can imagine in the extreme case, if you take the original matrix to be a rank n minus k minus 1 and only add a rank k Gaussian, the matrix is going to be singular with constant probability, or rather with probability 1. So you don't get any results. So this dependence on Sn minus k in the bound there is necessary. There's an analogous result in the case in which these random variables are complex, or everything is complex, and also in the case in which things are symmetric. So you constrain the rank k matrix you're adding to be a symmetric matrix, and the original matrix is also symmetric. The important generalization, though, or the most important generalization, is removing this constraint that the original matrix be of rank exactly n minus k. Of course, in practice, you might have a matrix which is close to rank n minus k, and you still want to sort of increase its smallest singular values by adding a rank k perturbation. And there is a generalization to that case as well, but the proof is more involved. So let me now give an outline of the proof. But first, let me just say that this is overall kind of the right dependence, where we're saying that the smallest singular value, the probability of the smallest singular value is less than some polynomial, is itself less than some polynomial. Okay, so this problem is hard because the randomness is shared across all the rows. This is something that's been touched on by the prior speakers as well, where these dependencies is kind of tricky. You know, in the dense case, understanding the distance between a row and the previous rows is sort of the crucial quantity they bound, and that can be done in a relatively straightforward way, or I shouldn't say straightforward, but it can be done using standard probabilistic techniques, or some interesting probabilistic techniques that fail in the case in which there's these dependencies. So this is a restatement of the theorem. And our idea is to decompose the matrix into blocks and apply the following lemma, which bounds the smallest singular value of a block matrix, and specifically writes it in terms of the singular values of each of the blocks and the Schur complement of the upper left block. So applying this, the proof of that lemma can be seen by verifying that, you know, this is the way you invert a block matrix, and applying the operator norm bound and submultiplicativity of the operator norm to each of the components, or each of the blocks. And decomposing our matrix in that way, we have a rather nice form. The first observation is that the starting matrix M can be replaced by a positive diagonal matrix, namely a matrix of singular values, and this comes from the rotational invariance of the Gaussian. You can write in terms of its SVD, and the U and V transpose of your Gaussian matrix kind of absorb of the Gaussian noise, absorb both of the orthogonal matrices. And that gives this block matrix a nice form. We end up with one of the blocks coming from M just being all 0. And that allows us to take that to be the upper left-hand block, and its Schur complement is easy to analyze, in particular because, so this is here on the screen, is the Schur complement, normal Schur complement, and the inner term actually just dies because this U sub k and V sub k, that's the k by k submatrix of the noise matrix, which you just take the first k column, or the first k rows of these matrices. So everything is square, so everything dies. In the context of this lemma, you can see the only terms you have left, that's sufficient to bound the Schur complement. And the only terms left are things in terms of the singular values of the U sub k and V sub k. Those are the only terms remaining. So all the terms are the inverse of this m prime, the positive singular values of m. So that's where the Sn minus k in the bound comes from. It's the smallest positive singular value of the matrix, and also the smallest singular values of these k by k dense Gaussian matrices. And the singular values can be bounded using usual techniques, and they're roughly like 1 over root k. So putting all those results together gives exactly the stated bounds. Okay. So to generalize for the rank n case is trickier, or in general, adding more ranks than your original matrix was rank deficient ends up being more complicated. In particular, if I just go back a couple slides, this inner term doesn't cancel. This U sub k and V sub k now are not square. So this term doesn't actually cancel out. And we actually adapt some ideas from the dense case and port them over. So I don't have time to go through the details of that proof. If you want to see the argument, you can check out our paper or talk to me afterward. And for the rest of the talk, I just wanted to discuss some next steps or some limitations, which is that.
Because we have like a 2 minutes.
Okay, perfect. So our result, you might ask if our result extends to other distributions, so other sub-Gaussians, and the answer is no. And we actually give an explicit example of a particular matrix where adding plus minus 1, so independent Rademacher or a rank k Rademacher matrix actually does not result in a large, small singular value. It's actually a singular with constant probability. And you also might wonder whether this effect is noticeable in practice, whether these constants are reasonable. And it turns out they are. And again, we just give a particular example of a really poorly conditioned matrix and show that adding a rank 1 perturbation actually results in a similar improvement to the condition number as does adding a dense perturbation. So the yellow and green lines are adding dense and rank 1 perturbations, and the blue line is the original singular value. You can see it degrades quite quickly with n. And of course, adding if you are explicitly constructing this rank k matrix, storing that and just using low rank matrix vector multiplication is much faster than constructing a dense matrix. So if your original matrix was sparse, for instance, then you are not blowing up the runtime of doing matrix vector multiplications by adding a noise matrix to it. So lastly, I'll give just kind of a very brief overview and say that there are some barriers to applying this directly to problems like the simplex method or k-means clustering or analyzing those algorithms. I'll just kind of skip over the argument, but you can check it out in the full analysis in our paper. And I'll just leave with some open problems, which is asking whether these bounds on the condition number are tight, and whether there are some other models in smooth analysis which might be of interest. So prior work has worked on the dense independent case. We are looking at the low rank case, and are there further models which could also be of interest? That's it. Thank you.
Thanks, Rico. Thanks. So our next talk will be distance estimation between unknown matrices using sublinear projections on Hamming cube by Arijit Vishnu, Arijit Ghosh, and Gopinath Misra. And Arijit Ghosh will be giving the talk. So Arijit, if you can just go over and stand next to the podium. Okay, great, now I can see you. And if you can unmute yourself.
Can you hear me now?
Yeah, now I can hear you.
Okay, thanks. Okay. Hi. My name is Arijit Ghosh. I will be talking about estimating distance between unknown matrices using projections on the Hamming cube. Not too many projections in the Hamming cube. This is a joint work with Arijit Vishnu, Gopinath Mishra. All three of us are from Indian Statistical Institute. Okay. So what's the problem that we are interested in? So we are given two n cross n matrices with real entries. Okay. So let's say we denote the entries by Aij. So the ijth entry of the matrix A will be denoted by Aij. Similarly, Bij for matrix B. And we are interested in the number of places there is a mismatch between these two matrices. Okay, so the number of, we want to count the number of pairs Ij such that Aij is not equal to Bij. Okay, so this is the question. Again, the matrix A and B are unknown. Okay. So as an example, let's take two matrices A and B just to understand what the definition of the distance is. So here I've underlined the places which is contributing to the distances. So there are 4 entries that are underlined. Okay, so the distance between matrix A and B is 4 here. Okay, so the matrices are unknown. So how are we going to solve the problem? Okay, so we have access to the matrices through some oracle. So this is a standard thing in property testing. So there's an unknown object and we have access to it through an oracle. Okay, so here the oracle is inner product oracle. We have oracles of two kinds. One is row inner product oracle, which is called row IP, and a column inner product oracle, which we call column IP. For the row inner product oracle, so you have an unknown matrix A. You give that oracle, row oracle, an index I and a vector V, index I between 1 to n, and a vector V, Hamming vector V, n dimensional. Okay, and the output will be the inner product between the ith row of A with the Hamming vector. Similarly, you can define the column oracle, column IP oracle. Okay, so what's the result? What is the main result of our work? The main result in this work is that we can design a randomized algorithm, okay, that takes two unknown matrices A and B as input, okay, where you have IP oracle access to both the unknown matrices, okay, and it takes an approximation parameter epsilon between 0 and 1. It returns 1 plus minus epsilon approximation to the distance between matrices A and B with high probability using n by square root d many IP queries. Okay, so d here I mean is the distance between the matrices. Okay, so it's sublinear in n. When the distance is large, is sublinear in n. Okay, so here O tilde hides polynomial factors in log n and 1 by epsilon. Okay, the interesting thing is this result we can show it to be tight also. Okay, so just let me give you just a brief outline of the algorithm very fast. So we will use two main ideas. Okay, two simple observation and two subroutines. So let me give you the observations first. So we define a set what is called NEQ set, not equal set. Okay, the not equal set is defined with respect to a matrix A, B, and an index I. And it basically gives you the set of indices where the ith row and the ith row of A and ith row of B differ. Okay, and we define the distance between the ith row of A and ith row of B to be basically the size of this NEQ set ABI. Okay, so the number of places ith row of A and ith row of B differ is defined as the distance between the ith row of A and ith row of B. So again, a simple example. Here we are looking at, we have matrix A and B. We have selected row 2. We want to know the NEQ set of AB2. The indices will be 1 and 2. And the distance is 2. Okay, so it's very simple to see that the distance between matrices is basically sum of the distances between the corresponding rows of the matrix. Okay, so what we do is we estimate this sum on the right, okay, by using two subroutines. Okay, and the subroutines basically use O tilde 1 many IP queries. Okay, so let me just give you a sketch of the subroutines. So there's one subroutine which is distance between rows subroutine. Okay, so you have these two unknown matrices A and B. The subroutine takes an index I and an approximation parameter alpha, and it will give you 1 plus minus alpha approximation to the distance between the ith row of A and ith row of B with high probability. Okay, so this subroutine crucially uses Johnson-Lindström's lemma. Okay? The second subroutine that we use is, again, we have these two unknown matrices. It again takes an index I and then again approximation parameter alpha, and it returns to you a random element from the set NEQ ABI. So it will return to you basically an index, a random index, where the random index where the ith row and the ith row of A and ith row of B differ. Okay, so here when I'm saying uniform, it's not uniform, it's almost uniform. Okay, close to uniform. Okay, so this subroutine basically used a stronger form of distance between rows as a subroutine. So both the subroutines crucially use Johnson-Lilje's. Okay, so let's give the algorithm. So for simplicity, let's assume that both the matrices are symmetric, and let's say we have a parameter T, which is an order 1 approximation to the, that parameter T is also given to us as an input, and which is an order 1 approximation to the distance between matrices. Here, see, remember, so what we are trying to do is get a 1 plus minus epsilon approximation. So just because you have a 60 factor, we are not completely done. We want a 1 plus minus epsilon factor approximation. So what we do is, again, go back to the sum. This is the sum we want to estimate. What we do is basically partition the row indices, okay, into buckets, okay, such that two indices, I and J, will be in the same bucket if the distance between the ith row of A and ith row of B and the distance between jth row of A and jth row of B are almost very close to each other, roughly of the same value. Okay. Once we have partitioned it into these buckets, okay, what we have to do is estimate the size of these buckets. Then we will be done with the estimation problem. Okay, so how do we do that? What we do is basically we take a uniformly random subset of n of size n by square root t. Okay, and we call that set omega, let's say. And now what we do is we run the distance between row subroutine on each index in the set omega. Okay, and partition them into buckets, okay, depending on their value. Okay, so if a bucket was large originally, okay, then that will be estimated by this sample, okay, just using standard Chernoff bounds. Okay, so by large here means greater than equal to square root t. Okay, but if it is smaller than that, the Chernoff bound doesn't work. We have to find an algorithmic solution there. There we use the second subroutine. Okay. So just before finishing the overview of the algorithm, I just want to say what kind of Johnson-Lilje
Can you try and wrap up in a minute or two?
Oh, okay, okay. So anyway, don't want to get into this. Okay, so so what we can show is that there is a matching lower bound for this problem also. Okay, so the upper bound we have matches the lower bound also. So using standard standard problem or disjointness problem in communication complexity, we show that n by square root d lower bound for estimating distance between matrices is stacked. Okay. Thank you. The full paper has many other sets of open questions. Please have a look. Thank you.
Thank you. Thanks. Okay, so our last talk for this session is L1 regression with Lewis-Waite subsampling by Aditya Parulakar, Dwight Parulakar, and Eric Price. And Aditya will give the talk.
So can you hear me?
Yes.
Okay. Screen share. Okay, and can you see slides?
Good. Yeah.
Awesome. So hi, I'm Aditya, and I'm going to be talking about L1 regression via Lewis-Waite subsampling, and this is joint work with Dwight Parulakar and Eric Price. So yeah, consider the problem of linear regression, where you have like n d-dimensional observations represented by matrix X and n corresponding labels Y. And you're trying to find beta that optimally, such that X beta is optimally close to Y. And we look at least absolute deviations regression, or L1 regression, where you're trying to minimize the one norm of X beta minus Y. In particular, we're going to be looking at the setting where you can see all of X, but you can't see all of Y, and you need to query specific elements of Y to see them. So you might be in a setting where, like, you have a lot of unlabeled data, but you might need like a human manually compute a label to see it. So that could be expensive. So the goal is to minimize the number of rows that you like sort of pay for. So concretely, you see the full training, you see the full data set X, but you don't see any of Y. And then you pick some index set I, and you can see Y sub I. And then you want to output an estimate beta tilde that is like approximately correct in the following sense, where the error on that estimate is very close to the error of beta star, which is the solution if you could see all of the labels Y. And so our strategy is just going to be to pick some distribution over the index set and just sample IAD M elements from this distribution. And we're going to be representing this sampling procedure using like a sampling and reweighting matrix defined as follows. So it's going to have M rows, and each row is going to have one non-zero entry at the ith index. It's going to have a non-zero entry at the ith index with probability p sub I, and the value is going to be 1 over p sub I, where the pi's are the distribution with which you're sampling. And this has the effect of just, so if X is a matrix with n rows, then Sx just like samples, like as the name suggests, samples and reweights rows from X into another matrix. And once we've sampled these rows, we query those labels of Y. So we look at we compute Sy, and then we just look at the minimizer on that sampled set. So the minimizer of Sx beta minus Sy. But we have to be a little careful picking the distribution with which we sample, because, for example, if you have a lot of data points that point in the same direction in the original, like in X, and you sample uniformly, for instance, then you might end up, your sample might end up taking a lot of those rows and not being very representative in other dimensions. And so your sample regression might not be too accurate. So you want to try to sample in some way that reflects the importance of the rows. And so to do this, we sample using what are called Lewis weights. And I won't get into the definition of what Lewis weights are for time's sake, but one of the key property of Lewis weights that ends up being useful is that they provide subspace embeddings. And so a subspace embedding is just a matrix that preserves norms in the column space of a given matrix. So, and there's a previous result that shows that if you choose S to be a sampling and reweighting matrix using the Lewis weights of a matrix, then with high probability you have that S provides a subspace embedding for the column space of X, which just means that Sx beta's norm is close to X beta's norm for all beta. And you need d log d over epsilon delta over epsilon squared rows to do so. So one thing that might be natural to try at first to show that our output beta tilde is good is to show that beta tilde is close to beta star, or that beta tilde minus beta star's norm is small. And this doesn't actually end up working, because in L1 minimization, the minimizer isn't even necessarily unique. So for example, in the d equals 1 case, sometimes L1 minimization is equivalent to computing a median. And so, the median of an even-sized list is anything between the two middle elements. And so if beta tilde and beta star can be like vastly different quantities themselves, then their difference, you can't really hope for their difference to be small. And this is the showing that beta tilde minus beta star is small is kind of key in the L2 setting. And it ends up being true because of some geometric considerations that don't end up working for L1. So instead, what we do is we consider the following diagram. So this is a sort of representation of our problem. So on the left, there's a drawing of Rn. This red line here, I don't know if you can see the cursor, but this red line here is a representation of the column space of X, and our point Y here. And then these green diamonds are like the L1 balls, or like L1 contours that like are expanding around Y. So the regression solution is like the projection using these these L1 balls onto the column space. So here's our true minimizer X beta star, if we could see all the data. And this is X beta tilde, which is our sampled estimate. And so yeah, similarly on the right we have the same thing, same drawing, but for the sampled space. So this is a representation of Rm. Here they're both drawn in R2 for simplicity, but just so the point is that we're not going to end up being able to show that x beta star minus x beta tilde is small. So instead, what we do is we look at these two blue distances, which are like the difference in the errors on beta star and beta tilde, and we show that those are approximately the same in the original setting and in the subsample problem. So in particular, that this blue distance minus this blue distance is small relative to x beta star minus x beta tilde. And so once you show this, you get the main upper bound, which is that if you have d log d over epsilon delta over epsilon squared rows, then you have a beta tilde that is approximately correct. And we also show a lower bound which has 3 instances, and it has like it has 3 instances, and it sort of like alternates like these 3 terms, 1 over epsilon squared d and log 1 over delta, and they all appear in the upper bound together, and then in the lower bound they just appear 2 at a time. And also, yeah, just some next steps, like there is a gap between the upper and lower bound. The upper bound has as well a log d, which the lower bound doesn't, and possibly some robustness guarantees of the L1 regression, like the subsampling, to showing some robustness guarantees of the subsampling. And also worth noting that this is concurrent work with Chen and Derasinski. And yeah, that's my talk. Thank you.
Thanks, Aditya. Okay, thanks to all the speakers again, and thank you all for attending. So please join us now in the discussion poster session, just outside of this room in the lobby. And yeah, that's all.
Are you able to see that? Oh, sorry, I think you're muted.
Can you hear me now?
Yeah, I can, yeah.
Okay, I came up to the mic. Yeah, so when you were sharing before, I couldn't see, I just saw a blank screen, a black screen.
Yeah.
Like it shows that you're sharing, but the screen is just black.
Oh, right. Oh, okay. Let's see if I can fix that.
Hi, Kwee. As soon as James is done figuring stuff out, feel free to come out and try out your sharing.
Can you hear me?
Yep, I can hear you.
Okay. Is there any particular place I should stand, or?
I think you have to be in that beige, that light beige area. I think that makes you a presenter.
Okay, great. All right.
Okay, and then if you want to try sharing your screen, you should be able to do that once you're in that beige area.
Let's see. Interesting. Sorry, 1 second.
Yeah, that's fine.
I guess I can share my entire screen. Can you see this?
Yes, I see all the slides.
Okay, awesome. Yeah. Okay. I've stopped. Have I stopped sharing?
You are still sharing. Now you stop sharing.
Okay.
Yeah, that looks good.
Cool. Awesome.
Oh, James, it looks like you are sharing now successfully, but I just see the room. I don't see your slides. I just see the room you're currently in.
Do you see the slides now, or just the room still?
I still just see the room.
Okay. Give me a second.
So the thing is, like, if you're full screening your browser, it only allows you to share like that browser. So you have to like come out of full screen, I think. It's weird. It doesn't allow you to like switch windows or something like that.
James, I still just see a black screen now.
Yeah. That is strange. I can see the black screen too.
Okay.
For some reason I can see my mouse.
I do see your mouse, but yeah, then it's just a black screen.
Okay.
Quickly, what did you do to make it work? Was there anything that worked for you?
I guess all I did was I just, instead of full screening my browser, I just made it like a window, and then that worked for me. I didn't do anything else that was particularly.
Yes, I see I saw your slides now, James. Yes, I can see those. So Zongchen, right now I just see your whole screen with the room. Oh, wow.
Oh, yeah, okay. Yeah, let me start. Can you hear me or?
I can hear you, yeah.
Oh, yeah, that's great.
Okay, but I did not see your slides. I just saw your browser that had the room on it.
Oh, yeah, I haven't opened the
Oh,
slides
okay.
yet.
That's fine, yeah. Okay. Hello, everyone, and welcome to this session 6 of Random. So just as a reminder, these talks are supposed to be 8 minutes long, so we likely won't have time for many questions, if any, during this session, but right after the session, if you go out to the main room, each speaker will be out there in a designated area, and you can go and ask them questions individually after the fact. So we will go ahead and get started. So our first talk in this session is by Kui Liu. He's going to be speaking about from coupling to spectral independence and black box comparison with the down-up walk.
Okay. Hi, everyone. Can you all see this? Okay, great. Yeah, thanks all for coming. So I'll be talking about sort of comparing like a very classical Markov chain mixing tool called coupling with a recently emerging tool called spectral independence. And that's how this yields some comparison inequalities with like the so-called down-up walk. And let me acknowledge that there's independent work by Blanca, Caputo, Chen, Parisi, Stepankovic, and Vigoda, which achieve essentially the same results. Okay. So in this talk, we'll be considering the sampling problem. So here, you're given some non-negative weight function on some finite state space omega, which is typically exponentially large. And your goal is to sample a random element x with probability proportional to mu of x. And for the purposes of this talk, we'll just mainly be considering graphical models. So these are distributions coming from graphs. So if you have a graph G, and your state space consists of all colorings of the vertices of the graph with some number of colors, say Q. And informally, the distribution is going to be described by local interactions across the edges of the graph. So let me just give you some examples. So one class example is the uniform distribution over proper colorings of a graph. So here, the local interactions just says that two neighboring vertices are not allowed to be colored the same color. Okay? And these distributions come up, everywhere in like statistical physics and machine learning. So a very classic method to solve this problem is to use a Markov chain Monte Carlo, and a particularly simple Markov chain is called the Glauber dynamics. So here, let me describe it as follows. So here you start with some coloring chi, and in each step you pick a uniformly random vertex v, and then you resample the color of that vertex conditioned on the colors of all the other vertices. So you should think of this as like a random walk on all colorings of the graph, and the sampling algorithm then just performs this random walk for some number of steps t, and then outputs the final state as the sample. Okay. Now, the number of steps you should take is called the mixing time. And the main question is, under what conditions is this mixing time upper bounded by a polynomial in the size of the graph? Okay. So a recently emerging technique, which is called spectral independence, has been very useful for studying this problem. So to define it, let me introduce this notion of an influence matrix. And this is a Qn by Qn matrix, where each row and column is indexed by a vertex color pair. And the entry is given by this difference of conditional marginals. So you should think of this as an influence, because you're asking how much knowing that, say, the vertex u is colored some colored red affects the probability that some other vertex v is colored some other color green. Okay. Now we say our distribution is spectrally independent if the largest eigenvalue, which is sort of like quantifies the total amount of correlations within this distribution, is upper bounded by eta, some number eta. So, and this sort of notion of spectral independence is really builds off a lot of work in this area called high dimensional expanders. So let me just give you a couple examples. So as the first example, let's say your distribution is a product distribution. So graphically, your graph has no edges, so there's no interactions across the vertices. And in this case, then the marginals are the distributions of the vertices are independent. So these marginals are the same, and so this matrix is a zero matrix, and so product distributions are zero spectrally independent. As a second example, if your distribution satisfies this statistical physics property called correlation decay, which is just the intuition that vertices that are far away from each other should have low influence on each other, and in fact, exponentially small influence on each other, then you can actually upper bound this spectral independence parameter by a constant independent of the size of the graph. And this is like the gold standard. You want, this is like what you're aiming for. Okay. And now there are like various other methods that are known to that allow you to bound this spectral independence parameter. What's interesting about spectral independence is that if you strengthen it to encompass all conditional distributions, then you can deduce a very strong mixing time bounds. So in particular, if your distribution comes from a bounded degree graphical model, and your spectral independence parameter is upper bounded by a constant independent of the size of the graph, then you can deduce that the Glauber dynamics mixes in optimal n log n steps. Okay. And so this is optimal dependence on n. And in general, if you don't have this assumption that your distribution comes from a graphical model on a bounded degree graph, then you can still deduce polynomial mixing time bounds. Okay. So that's why spectral independence is useful. But sort of in this work, what we ask a simple question, which is just how does this new technique of spectral independence compare with more classical tools for proving Markov chain mixing? And in this work, we really focus on this on the classical tool called coupling. Okay, so let me just give you a very, very quick overview of what coupling does. So in coupling, what you imagine doing, so coupling is a technique which sort of allows you to sort of bound the total variation distance of your Markov chain from the stationary distribution in a very direct manner. Okay, so what you imagine doing is you run two copies of the Markov chain, two faithful copies of the Markov chain. And what you want to do is you want to couple the transitions of this Markov chain such that you want to sort of induce, like make these two independent copies sort of collide with each other. Okay, and sort of the faster you're able to make them collide with each other, you can then do stronger and stronger mixing time bounds. Okay. So in particular, for instance, if you can show that they say the expected distance between successive iterates of the coupling is contracting by some factor in each step, then you can deduce very strong mixing time bounds. Okay? And this is also related to a notion called Dobrushin influence or Dobrushin uniqueness, if you've heard about it. And so more concretely, our question is like, if you can show that, say, you have a good coupling in some sense, say a coupling that's contracting in this sense, does this imply spectral independence, or how does it compare with spectral independence? Okay. And so now let me sort of state our main theorem, or at least informally. So suppose I have some Markov chain, any Markov chain at all, just with the correct stationary distribution mu. And I'm gonna impose that it satisfies two assumptions. So the first assumption is locality. So in each step, the Markov chain is allowed to change the colors of at most L many vertices. Okay, so for the Glauber dynamics, L equals 1. And I further impose that it satisfies some weak coupling condition. So there exists some coupling of the Markov chain such that in expectation, the distance between successive iterates doesn't necessarily contract in each step, but is infinitely summable. So this infinite sum is finite, and in particular, it's bounded by, say, some constant times n times the distance between the starting states. Okay. Then if you have these two conditions, then you can deduce a bound on the spectral independence parameter. And in particular, if these, say, this C and this L are constants independent of n, then you can deduce, at least in the bounded degree graphical model case, you can deduce optimal mixing of the Glauber dynamics, and you can deduce polynomial mixing in general. Okay, so let me just to help you parse this weak coupling condition a little bit, if you have a stronger condition such that, for instance,
quickly, I'm going to ask you to wrap it up in the next minute or so.
Yeah, in the next minute, yeah, I'll be done. This is the last slide, basically. So if you, for instance, have a slightly strong condition that, say, the expected distance is contracting at each step, then you can upper bound this constant C by, say, 1 over alpha. But you can allow for something much weaker. For instance, you can allow to contract by a constant factor in roughly order of n steps in expectation. That's fine. Okay. So you should really think of this as some kind of comparison inequality where you say that if you have some coupling for some Markov chain that is good in some sense, then you can actually deduce a rapid mixing result for the Glauber dynamics itself. So it's in that sense that this is a comparison inequality, and this has some nice nice implications. So for instance, this gives some resolution to the so-called Paris-Ditali conjecture for the log Sobolev constant under curvature assumptions, at least for graphical models on bounded degrees graphs. And it also gives n log n mixing with optimal mixing times for sampling proper colorings when Q is larger than this threshold based on the maximum degree, which was not known before. Okay. And I'll stop here. See the full talk for the more details. Thanks.
Okay. Thanks, Kwee.
Let me stop share.
Yeah, so James, if you want to come up.
Hello?
Yes, we can hear you. Great.
There we go. Okay.
So our next talk is going to be by James Stewart, and he's going to be talking about fast mixing via polymers for random graphs with unbounded degree.
Okay, thank you. So hi everyone, I'm James Stewart, and I'm going to be presenting our paper, Fast Mixing via Polymers for Random Graphs with Unbounded Degrees. And this is joint work with Andreas Galanis and Leslie Goldberg. And we give some efficient algorithms for the low temperature Potts model on a class of random graphs with unbounded maximum degrees. So the Potts model is a model on colorings of a graph G. We have some integer Q, which is a number of colors or spins, and we have a strictly positive real parameter beta. And each Q coloring of G is weighted as e to the minus beta times the number of bichromatic edges that coloring induces. So colorings with lots of bichromatic edges are weighted the least, and colorings which are, say, mostly monochromatic are weighted the most. And beta can be thought of as the kind of penalty incurred for seeing a bichromatic edge in a coloring. So the Potts model has a partition function z of beta, which simply counts the total weight of all of the Q colorings of G. We also have a Gibbs distribution, which is a probability distribution on colorings, where each coloring has probability proportional to its weight. And here, z, the partition function, is a normalizing factor. So the two computational problems that we're going to be interested in are firstly approximate counting. So given a graph G, we'd like to output an approximation for the partition function of the Potts model on G. And secondly, we have approximate sampling, where given a graph G, we'd like to output an approximate sample from the Gibbs distribution of the Potts model. So in terms of existing algorithms, it's known that on graphs whose maximum degree is at most some fixed constant delta, Markov chains such as the Glauber dynamics mix rapidly when beta is small with respect to Q, the number of spins, and delta, the maximum degree of the graph. When beta is large enough with respect to Q and delta, the Glauber dynamics mixes exponentially slowly, and in fact, it's computationally hard to approximate the partition function of the Potts model. And so in light of this slow mixing and hardness, recent attention's focused on more restricted classes of graphs, namely bounded degree expander graphs. And this is an interesting class of graphs because a random regular graph is an expander with high probability. So recent work of Jensen, Kivash, and Perkins has given efficient approximate counting and sampling algorithms for the low temperature Potts model on the random regular graph. So this is when beta is large enough with respect to Q and delta. In a similar vein here, we give efficient algorithms for the low temperature Potts model on a class of random graphs, so sparse random graphs of unbounded maximum degree, but bounded average degree. And our algorithms apply when beta is large enough with respect to Q, the number of spins, but instead of the maximum degree, the average degree of the graph. So the specific class of random graphs that we consider can be described as follows. If we have an integer n and a degree sequence x bar, we choose a graph uniformly at random from the set of all simple graphs having degree sequence x. And the degree sequence should satisfy a couple of mild conditions. The first of these is a condition on the degrees. So the degree of every vertex should be at least 3 and at most n to the power rho, where we set rho to be 1/50, but in general this can be relaxed. It just cannot be made linear in n. And the second condition is a sparsity condition, which requires that the sum of the squares of the degrees of the vertices is linear in n, so at most d times n. Okay, so our main theorem says that for the ferromagnetic Potts model, if beta is large enough, then we have a polynomial time approximate sampling algorithm for the Gibbs distribution of the Potts model on G. And we have an efficient approximation algorithm, so an FPRAS, for the partition function of the Potts model on G. And both of these algorithms work with high probability on random graphs chosen uniformly at random with degree sequence x bar, and x bar should satisfy the two conditions that we saw on the previous slide. So here with high probability means with probability 1 minus little o of 1 over the choice of G. So the probability of success is tending to 1 as n tends towards infinity. I should also say that we expect these techniques don't just apply to the ferromagnetic Potts model, but should be generalizable to other spin systems, and in fact general spin systems in the strong spin interaction regime on bipartite random graphs, as is the case in the delta regular world. The lower bound on beta is something like d log q. So here we're relating beta to the average degree of the graph, which is in contrast to previous work where beta is related to the maximum degree. And the running time of the FPRAS, for example, is n squared log cubed n. Okay, so to give a brief overview of our sort of high-level approach, the key is that at low temperatures, so when beta is large enough, a typical sample from the Gibbs distribution of the Potts model looks mostly monochromatic. So it might look something like the coloring in the picture, which is mostly red apart from a few small islands of non-red vertices. And what this means is that the state space, so the set of all possible colorings, is effectively partitioned into Q, what we call phases. So we have each one phase per color, and the red phase, for example, contains the colorings which are mostly red. And it's also possible to show that the coloring which isn't dominated by a single color, so which isn't in the phase corresponding to any one color, these colorings contribute a negligible amount of weight to the partition function. And so we can effectively just throw these out and ignore them. So this means we can just focus on a fixed phase. So let's say the red phase, and try and approximate the total weight of all of the colorings, which are almost all red. So to capture the red phase, we appeal to what are known as polymer models. And polymer models allow us to kind of rewrite the partition function of the spin system in terms of the deviations that spin configurations take from the ground state. And a polymer model induces a partition function and a Gibbs distribution of its own. And it can be shown that the problem of sampling from the Gibbs distribution of the Potts model simply reduces to the problem of sampling from the Gibbs distribution of an appropriately defined polymer model. So this is the main challenge. And to sample from the Gibbs distribution of a polymer model, we appeal to a Markov chain or a variation of a Markov chain known as the polymer dynamics. And we show that this Markov chain mixes rapidly, subject to a condition on the weights of the polymers. So in the specific case of the Potts model, ensuring that this condition is satisfied essentially amounts to making beta large enough. So from here, we can efficiently sample from the Gibbs distribution of the polymer model, which easily gives us an algorithm for sampling from the Gibbs distribution of the Potts model. Okay, I'll leave it there.
Thanks, James.
Thanks.
Can you see my slides and myself?
Yes, I can hear you and I can see your slides.
Okay, perfect.
Okay, so we will move on to our next talk. So this next talk is given by Zusheng Zhang from Penn State. He's going to be talking about the critical mean field Chase-Matcha dynamics.
Hi, everyone. I'm Shushan. This is based on the paper Critical Mean Field Chase-Matcha Dynamics that is a joint work with Antonio Bianca and Alistair Sinclair. And let's see. So we are talking about the random cluster model that is a probability distribution over a subgraph of a given graph G. And we call subset of edges configuration. Every configuration could show up in this probability model with weights proportional to this expression. That is p to the power of number of edges in the configuration times 1 minus p to the power of missing edges from this configuration times q to the factor of C of A. And C of A denotes the number of connected components in this subgraph induced on configuration. For example, here you have 2 connected components and you have only 2 edges in your configuration, but you have 4 missing edges. So their weights function proportional to q squared, p squared times 1 minus p to the 4th. And here you have 1 less edge in the configuration and you have 1 more connected component. So the factor of the power to p is 3 and the power to 1 minus p is 5th, and you have only 1 edge. That will be our model, and this is an important model because it unifies a couple well-known probability model. And when q equals to 1, you have the bound population where you just have each edge independently added into a subgraph with probability p. When q is greater than or equal to 2, this is deeply connected with the q-state parts model. When you have q approach to 0, the limit of our model give you a uniform spanning tree, uniform spanning forest, and uniform connected subgraph. When G is a complete graph, we call this mean field random cluster model. The main subject of this talk is about the Chase-Matcha dynamics. That is a Markov chain conversion to the random cluster model distribution, and generalize the Swinson-Wang dynamics used to sample the parts model from integer domain to the real greater than or equal to 1. Natural motivation of this dynamics is to sample configuration. Of course, they also give you an algorithm, approximate algorithm to the partition function of the random cluster model. They help study the interplay between phase transition dynamics and time. It is also a stepping stone to understand other more natural Markov chains. Okay, now let's describe the steps of the CM dynamics through an example. Suppose on the left, we are given a configuration. And the first thing we're going to do is to activate each of them independently with probability 1 over q. So this, as an instance, we activate this one, we don't activate this one, and we activate each one of these red things. So we label these activated connected components by red, and for the rest, we just give them a color of green. And the second step is to remove the edges from these activated connected components. Now this step leaves us with 14 isolated vertices. And the third step is to do the population on top of this activated subgraph. So for each edge between 2 red vertices, we give them an edge with probability p independently. And that gives us 6 edges on the right, and that gives us also a few new connected components. And that's the end of one step. And at this step, we don't differentiate anymore between gray connected components and red connected components, and we just return the whole thing as one configuration. Note that all this is about one step, and we're gonna take many steps to reach the random cluster model. And how many steps are we gonna take? That is measured by the standard measure of conversion rates called mixing time. That is the number of steps for your Markov chain to be close to your stationary distribution, assuming you start from the worst configuration. Let me reparameterize the model. We're going to write the product of P times N by zeta, and this result given by Bogdash, Grimek, Jensen, followed by Luxa and Luxa, shows that there is a critical value for zeta. We call zeta of Q, and the value of zeta of Q is different depending on the value of Q. Especially when Q is greater than 2, this value falls inside so-called metastability window. Recall the same dynamics defined for all the reals greater than or equal to 1. And for all this Q, zeta is between this metastability window. We denote the endpoint of the window by zeta L and zeta R. And the mixing time of CM dynamic has been studied by a few papers. Blanca Sinclair, together with Geiseri, Lubitz, and Pirish, complete the analysis for the regime Q greater than 2. Outside the metastability window, you have mixing time roughly log n, and at the left endpoint, you have mixing time n to the 1/3. Inside the metastability window, you have exponentially large mixing time. And when Q equals to 1, this is a trivial, you mix in one step because that's just a bump population. Blanca Sinclair also give a log n mixing time for all the non-critical zeta for Q between 1 and 2. At a special point when Q equals 2, the CM dynamics really close to the Swinson-1 dynamics. So long Lipman-Ning's empirical result for Swinson-1 applies to this scenario. You have n to the 1/4. And so the only remaining interesting case is when Q between 1 and 2 and the zeta is critical. And that is precisely what our work is about. Our first result gives this mixing time bound by log n times log n in the critical regime on the complete graph. Since there's also a log n lower bound, this result is tied up to a factor of log n. And in fact, we can replace this extra factor of log n by any function that going to infinity. So actually, we got much tighter results than what appears here. And our second result is concerning the Gaussian dynamics on the random cluster model. And when by Gaussian dynamics, I mean you pick an edge randomly, and then you add the edge or remove edge if the edge exists according to this probability. We show that mixing time of Gaussian dynamics can be bounded by the CM dynamics with this extra factor. This is like a general comparison inequality, and it was shown in Blanca Sinclair, but the extra factor is n to the 4th. We improve it to n cubed. And yeah, that's all of our results. And the natural step to do in future is to close the gap for both mixing time and potentially applying this technique to other graph. I won't have time go inside the proof, so you can talk to me in the poster or just watch the recorded video. And thank you for attention.
Yep, thanks, Xusheng. We actually do have time for maybe one question. If anyone has one question now. Okay, well, we don't have any questions now. There is, of course, time for plenty of questions after, so I guess we will just move on.
Can you see my slides?
Yes, I can see your slides and I can hear you, which is great.
Great.
Okay, so I guess we'll just go ahead and get started with the next talk. So this next talk is by Zongchen Chen, and he's going to be talking about the Swinson wing dynamics on trees. Go ahead, Zongchen.
Yeah, thank you. So I'll talk about the Swinson wing dynamics on the complete tree. And this is joint work with Antonio Blanca, Daniel Stefankovic, and Eric Vigoda. So in this talk, I'll discuss global dynamics, which is the Swinson wing dynamics for the pulse model. And let me first introduce to you the definition of the pulse model. So we will be given a graph G and also a set of spins or colors, which is represented by 1, 2, 2Q. And by a configuration, we mean an assignment of spins or colors to all the vertices of the graph. And also there's a parameter beta, which is a real number and controls the characterize the interaction strengths between adjacent vertices. And this parameter is also called the inverse temperature. And we will be considering the Gibbs distribution, where every configuration, which are assignment of spins, will have a probability density that is proportional to exponential to beta times the number of monochromatic edges. So here, M of sigma represents the set of all monochromatic edges, which are the edges whose two endpoints receive the same spin. And the function, this value z, is the normalizing constant for this Gibbs distribution, which is also called the partition function. And in particular, when Q equals 2, where you have two spins, this is called the Ising model. And usually people use plus and minus for the spin set for the Ising model. And also, it's not hard to see from the definition that when your parameter beta is a positive number, then your distribution will prefer monochromatic edges. So when you sample from the Gibbs distribution, you are more likely to see adjacent vertices receive the same spin. And this is called the ferromagnetic model or attractive. And when beta is smaller than 0, it is called anti-ferromagnetic or repulsive, where the model basically prefers bichromatic edges. And the problem we will study in this talk and in our paper is how to generate samples approximately from the Gibbs distribution of the pulse model. And we will actually focus on the complete D-array trees. These are the trees with like a fixed height, and every non-leaf vertices will have exactly D children. And the reason we study the trees is that it is perhaps one of the easiest class of the graph, but the methods like MCMC methods for sampling from the pulse model is still unclear. And also it is an example of a non-amenable graph in contrast to the other graphs that we'll study, like the integer lattice. And also a lot of statistical physics and computational phase transition and thresholds are studied and derived on the trees. And also trees are used for establishing the computational hardness for a lot of approximate counting problems. So the trees are actually important in the study of spin system. And so this talk and our paper, we study MCMC method for sampling from the pulse model on the complete D-array trees. And to state our result, we will also what we actually do is try to bound the relaxation time and the mixing time of a global MCMC, which is the Swinson dynamics. And here, the relaxation time represents the inverse of the spectral gap of the transition matrix of our Markov chain, which corresponds to, which basically describes your convergence time when you start from warm start. And meanwhile, the mixing time is the number of steps it takes to be within a small total variation distance, even when you start from a worst configuration. And so one important thing in our paper is that we are very interested in the trees with boundary conditions. So by a boundary conditions, we mean that in our complete D-array tree, all the leaves will be fixed to some configuration. And we will be mainly focusing on like two boundary conditions. The first one is called the monochromatic boundary condition, where we fix all the leaves to some color, let's say red. And the other is arbitrary boundary condition. So basically, we will fix the leaves to some arbitrary configuration, and we want our Markov chain to be rapid mixing under any boundary conditions. And the boundary conditions are also very important in the study of like Gibbs measure for spin systems on the infinite trees. And it's also important for like understanding the different phases of the Gibbs measure. And so next, let me introduce the Swinson dynamics, which is sort of already mentioned in the previous talk. So the Swinson dynamics is a Markov chain to generate a configuration or a sample from the Gibbs distribution, and it works as follows. In every step, we always maintain a configuration like a spin assignment, and what we will do in each step is that we will first generate a random subset of edges, and we do this by first remove all the bichromatic edges. These are the edges with two endpoints receiving different colors. And the next, for all the monochromatic edges, we will basically do a percolation. That means we will, for every edge, for every monochromatic edge independently, we will include in our random subset with certain probability. And this is one step. This is like the step of generating a random subset from the current configuration. And the second step is to recolor all the vertices. And we do this by one component at a time. So we will take for every component, every connected component of the resulting subgraph given the edge set you sampled. So if your component contains a leaves, let's say this component here, whose vertex, so since it contains a leaf whose spin is fixed by the boundary condition, we will make this component remain the same. So all the vertices will receive the same color as before. So we make no changes. And for all the other components, these are components that does not contain leaves or even like isolated vertices. For these components, we will pick a color uniformly at random and assign this color to every vertex in this component. So we will do one step of this chain, and we get a new coloring of the vertices. And that's it, one step. And it's not hard to show that with this like percolation probability, this dynamics will eventually converge to the Gibbs distribution. And also, we can see from its definition that this dynamics is a global Markov chain in the sense that in every state, a constant fraction of vertices will change their spins in contrast to the local chains like the global dynamics, where in every step you only update one vertex. And also this chain is very easy for parallelism. And also it is conjectured or experimentally shows that it is efficient even at the low temperature when your parameter is large, which is typically a hard regime for the global dynamics, for the global dynamics. And so here is the statement of our main results. So we study the ferromagnetic Ising and Potts model on the complete diary tree. And we show that the relaxation time of the Swinson dynamics I just mentioned is order 1, and the mixing time is order log n. And in the following cases, the first is that you have a monochromatic boundary condition where all leaves have the same color and the beta is arbitrary. And second is that the boundary condition is arbitrary and beta is upper bounded by some threshold. So here, since we allow like an arbitrary configuration on the leaves, there must be some restriction on the value of the beta. And in particular, the beta U is the tree uniqueness threshold. And our bound actually goes beyond the uniqueness threshold when your degree is sufficiently large compared to the number of colors. And also, this result, the parameter regime for global matches our result matches the parameter regime for the global dynamics, which proved by Martinelli, Sinclair, and Weiss. And the more interesting thing is that we actually use this to spatial mixing conditions of their paper. So basically, they propose two mixing conditions called the variance mixing and entropy mixing, which both captures the exponential decay of correlation between a vertex and a subset of vertex. And they show that these two conditions implies tight bond on the mixing time and the relaxation time for the global dynamics. And what we show is that these two conditions also can be used to show the mixing time bound and relaxation time optimal bounds for the Swinson wind dynamics. And we prove this by using a certain tensorialization of these two conditions, and also using some spectral interpretation of the variance mixing and entropy mixing conditions. And that's like a very high level proof approach. And I think I'll stop now. Thank you.
Yeah, thanks, Songten. And let's also thank all the speakers in this session. This was a great session. And so just to remind you, for questions, all the speakers from this session are going to be outside in the main hall. There's going to be posters with the titles of each of the talk, and you can find the speakers for the corresponding talks there to go and ask any questions that you might have. So thanks all of you for coming and for sticking around for this last session of the day.
Thank you.